Hi everyone. It's my first time in ICTS and I'm really delighted to be here in this wonderful campus and in this great workshop on gravitational waves. So this is a work that I did with two of my very good students and Somen Basak, who is at IISER. So I'm going to talk about it in a while, but let's start with some short introductions. Okay. So early universe is sort of a natural high energy physics laboratory in nature, and we can extract physics beyond the standard model as well as beyond standard model cosmology from the early universe. So in cosmology, in general, we have two types of observables, primordial relics, such as the most famous ones are, for example, helium nuclei. There could be primordial black holes or cosmological solitons like oscillons, strings, domain walls, etc. We also have propagating signals like cosmic photon background, which we call CMB. We could have cosmic neutrino background someday. I mean, we could detect it someday. And of course, we have stochastic gravitational wave background in cosmology. And by studying their correlations, by detecting them and studying their correlations, we can understand what were the initial correlations, and from there we will detect new physics. Okay. In particular, the history of the universe is pretty well known towards relatively late universe. So from Big Bang nucleosynthesis all the way till today, the history is overall well known. Of course, we need to understand dark matter, dark energy, and Hubble tension. However, the history of the universe prior to Big Bang nucleosynthesis is not very well known. In particular, CMB sees about 6-7 e-folds of expansion during inflation, if inflation is correct. And so a lot of inflationary expansion is left undetected. And Sriram must have given you a talk on this, and Jan Massimo would also give you a detailed set of lectures on this. So I'll leave that part. I'm going to focus about post-inflationary evolution of the universe from the end of inflation all the way till Big Bang nucleosynthesis. So CMB is one of our best probes of understanding early universe when combined with other probes like BBN, large scale structure, and BAO. And when we look at this wonderful map of CMB temperature fluctuations, there are two questions that come to our mind. One is what created this plasma with all of these degrees of freedom? And the second is what created these fluctuations? And both the questions are very well linked to cosmic inflation. So in particular, the single field slow roll inflationary scenario has been very successful. It's a minimalistic model where we have GR and a scalar field, canonical minimally coupled. In such a theory, you would get a background expansion which is exponential, nearly exponential, if your slow roll approximations are correct. And then on top of this background, you will generate fluctuations. And these fluctuations are usually present in 2 degrees of freedom. Well, 3 degrees of freedom, but 2 fields. One is a scalar field, zeta, which I'm not going to talk about much. The other one is the transverse and traceless tensor fluctuations, which I'm going to talk about. Okay. And under this famous slow roll approximation, at least on large scales, early enough times during inflation, the scalar fluctuations take nearly approximately the form of a power law, and so are the tensor fluctuations. Okay? And for the scalars, we have detected both the amplitude of fluctuations as well as the tilt. And the tilt is guaranteed to be small in slow roll because of slow roll approximations. We haven't seen the tensor so far, so we are waiting to see the tensor fluctuations. In fact, the tensor fluctuations are usually characterized in terms of tensor to scalar ratio R. The typical prediction of this single field slow roll inflation is the following. You have tiny fluctuations which are nearly scale invariant and very Gaussian. The current observational constraints are the following. This is your scalar spectral index, NS. This is the tensor to scalar ratio. Most of the data is here. And if we interpret this data in terms of single field slow roll inflation, then it points us to the following. It says that single field works pretty well, single field paradigm. And the potential, which sort of explains the background during inflation, better be concave, and preferably asymptotically flat. So these are very, very interesting outcomes of observation so far. Great. But that's usually celebrated as a success story for inflation, but there's a lot to be known before we are sure that inflation happened, and it's theoretically, it's analytically understandable formalism. In particular, theoretically, we don't know the origin of inflaton field. We don't know whether single field or multi-field is correct. Okay. We don't know how the inflaton field exactly interacts with other fields, including standard model. Also, what are the fundamental signals which can tell us for sure that inflation happened? So these are all open questions. Similarly, observationally, we have to see the B mode polarization, which Subhendra is introducing us this week. We can also see gravitational waves from inflation using GW observatories, which is what I'm going to talk about in the rest of the slides. We have to detect primordial non-gaussianities carefully, both from large-scale structures, CMB, as well as 21 centimeter fluctuations. Phenomenologically, I am primarily a phenomenologist. So what are the predictions for primordial gravitational waves? How does the inflaton field decay exactly and universe reheats? Small-scale inflationary dynamics against Sriram-Stock and Gianmassimo-Stock, and primordial non-gaussianity. So all of these are open questions. My talk is about these tick marks, gravitational waves from inflation. In particular, first-order vacuum gravitational waves from inflation. So inflation excites tensor fluctuations. These are very long wavelength tensor fluctuations. And if we detect them via CMB B mode polarization, then we would set the energy scale of inflation. So we'll have a good information about the energy scale of inflation. That's great. But then these gravitational waves, which are created, let's think of the output of inflation at the end of inflation being propagating through the history of the universe to reach us today. Then it's sensitive to what the universe was doing in between the end of inflation and today. Okay. So in that sense, they would encode the expansion history of the universe. And we are interested in both the amplitude and tilt of these gravitational waves. As long as the wavelengths are long enough from the end of inflation horizon scale, we are okay with it. Even though there is something happening during the end of inflation, if you look at long wavelength gravitational waves, long enough. They don't have to be CMB like long. Great question. Okay, the way, since there are students here, I will show two slides, the way we compute vacuum tensor fluctuations during inflation. So the tensor fluctuations over this is the quadratic action if I drop all the interactions. And I can write it in a particular gauge in which we have the plus and cross polarizations. And then I'll quantize these fields basically. So first of all, I can write it as a summation of plus and cross polarizations in this way. So I go from a tensor field to two scalar fields basically, H plus and H cross. And then I do this matrix which Starobinsky did. I change it to Starobinsky variable, then reduce it to this action. This looks like action of a scalar field which has a mass in Minkowski spacetime. And I know how to quantize Minkowski spacetime. I can calculate vacuum fluctuations in Minkowski spacetime. So these fluctuations, they actually act as a massive scalar fields with tachyonic mass. Well, this V is not observable, it's H which is observable. So H is not tachyonic. Great, and then you can compute the power spectrum by just knowing how to compute vacuum fluctuations of a Klein-Gordon field in Minkowski spacetime. So it's easier, and that's how this formula pops out in this calculation. Okay. And there is a consistency relation that if you measure tensor to scalar ratio, and if you somehow measure the tilt of your tensor fluctuations in a single field slow roll inflation, in the standard single field slow roll inflation, you will have this consistency relation. So this is what you produce at the end of inflation. That's your initial conditions for gravitational waves. These fluctuations are produced initially on sub-Hubble scales. They are stretched outside and they are frozen all through the time when they are outside the Hubble radius, and they enter the Hubble radius and propagate as primordial gravitational waves. Okay. So the inflationary output is fed into the input of hot Big Bang phase through this period of reheating. These tensor fluctuations would become our gravitational waves, just like scalar fluctuations become acoustic waves or later large-scale structure. And Subhendra also showed us this equation today, where the tensor modes in an expanding universe satisfy this equation. If I treat, imagine that this is inflation, this is reheating, and this is, let's say, radiation domination. If I feed the output of inflation into radiation domination, it has to pass through the epoch of reheating. And usually, people would model the epoch of reheating as a single constant equation of state W, or W reheating. In that case, the expansion is just trivial. One can work it out, how it varies as a function of conformal time tau. And then you can put it back and solve this simple equation in terms of Bessel functions. So you'll get a general solution. And you say my initial conditions are created by inflation, that would solve for your undetermined coefficients, and you know the gravitational waves from inflation. And then you propagate them through radiation and matter domination and calculate it today. Once you know what is H, from H you can compute omega, which again Gopu was telling us a few minutes ago, which is the density of gravitational waves per log interval of frequency scaled by the critical density of the universe. So I'm just showing it, I'm not going to explain, these are standard stuff. But for students who have never calculated it, this is how you calculate. So at any time, omega GW, the spectral energy density, is related to the power spectrum of tensor fluctuations at that time with a transfer factor. In particular, if I simplify this formula, then those tensor fluctuations which enter the Hubble radius during radiation-dominated epoch, they would have a flat spectrum. And those which enter in a matter-dominated epoch, they would have a tilt of slope -2. And those which enter in during the high-frequency ones or small wavelength ones, which enter during reheating, could have any slope depending on the equation of state of reheating, which we don't know. Okay, we are modeling it by a single equation of state. In particular, if the equation of state is stiff-like, it's greater than 1/3, then you have a blue tilted gravitational wave, so it can reach your detectors and you can detect it. That's the wisdom. Okay, otherwise it's either flat or going down. So blue tilted gravitational waves, which are phenomenologically interesting, would correspond to stiff equation of state during reheating. So in 29, well, this is a result which is known since, the first calculation was done by Bruce Allen and Varun Sahni in 90s and late 80s. It was well known. But in 2019, Danny Figueira and Erwin Tanin, they did a detailed analysis of what should be the duration of reheating, the temperature of reheating, and the equation of state, show that you would see an observational signal in any of the future detectors. In particular, they focused on LIGO and LISA. And their conclusion was the following, that the tensor to scalar ratio should be high enough. The current bound is R is smaller than 0.036. So as long as it's not much smaller than that, it's good. Your equation of state should be stiff-like, okay? And reheating temperature should be low. These are obvious facts. Okay? However, people like me who study reheating of the universe, the physics of reheating, we realize that reheating is an extremely complicated process. Okay? It goes through lots of changes in between. For example, the initial stages are non-perturbative. It could be non-perturbative, and so the physics is different. And then in the intermediate stage is unknown so far, and maybe the final stages are perturbative, but they sometimes go through turbulence. So the whole period of reheating could be complicated, and it could be long. Okay? In standard calculation, people assume that reheating is an instantaneous process, but it could be a very, very long process lasting for 20, 25 number of E-folds. So it's not enough to just model reheating by a single equation of state. In fact, during reheating, you can also form transients and solitons. Right. So first point, reheating is complicated. So the equation of state could show variation. The second thing is, early universe may have lots of phase transitions, and we have been hearing so many talks on phase transitions in the early universe. So again, the equation of state suffers. For example, in the simple QCD phase transition, the equation of state drops. Okay, and that's well known, of course. So we sort of try to do the following. So it's Atul and Mohammad Shafi who are my students. In fact, Atul has just been selected to go to CISA in Trieste to do his PhD. So we sort of collaborated together and tried to understand what would be the signature of gravitational waves when you have many epochs of reheating. Okay? To be particular, we modeled from inflation to the final radiation domination, we modeled the history of the universe to be consisting of n number of epochs of equation of state W1, W2, W3, etc. And for the first part of our work, we remained completely agnostic. That we didn't take any model. We let W1, W2, Wn vary in between -1/3 and +1. Okay? And we modeled transition between one equation of state to the other in an instantaneous way. So via theta function, Heaviside theta function. Okay? That's a strong assumption, but we wanted to do analytical calculation, so we did this. And then we used Israel junction matching condition to calculate the gravitational wave signal, okay, which is a standard calculation. We did another assumption, which is the following, which is important, especially in light of Subhendra's talk. We assume that suppose in the next 10 years, Lightbird or CMB stage 4 would see some signal in the B mode polarization. Okay, that's a good best case scenario. Therefore, we took our tensor to scalar ratio to be 0.001. Okay, that's what you can see in the next 10 to 15 years. So given that you would see some signal from inflation on very long wavelength scales that Subhendra is talking about, the question we asked is, what should be the reheating equation of state and the duration of reheating, etc., so that you would have an observed signal in the rest of the detectors, either ground-based or space-based. So that's the question that we were addressing in this work. So for the first epoch after inflation, you feed in the inflationary output into the input of these gravitational waves, as I said. And for the rest of the epoch, you do Israel junction matching. So both the metric fluctuations as well as their derivatives, they both are equal. It's both continuous and differentiable. And then you go through one epoch to the other, etc. It's a standard calculation, but it's a long calculation. Just to show you a particular expression, for example, the unknowns in the Bessel function, the coefficients, of some epoch which is m plus 1th is related to the coefficients in the mth epoch via this. It's a clean calculation. Okay, in fact, you can do it by hand. You don't even need Mathematica. And so take this and compute omega GW. Okay, and I'm just demonstrating you for a few cases here. Here is the trivial case which everybody does, which is a single equation of state. Here we have two different equations of state with one transition in between. There are three equations of states here, and there are four here. Okay. So the usual wisdom of that, if you have a stiff equation of state, then you might go into the BBN constraints which are here, is not always correct. If the equation of state initially is, let's say, matter-like, a scalar field is oscillating and then something else rolls down, then you may have initially matter-like and later you may have a kinesin phase or a stiff equation of state. And you'll be completely safe from LIGO and BBN constraints, and yet you'll have a detectable signal. To give you another illustration, suppose that there are two equations of states during reheating with one transition in between, and if I assume that the reheating temperature is low enough, 10 MeV, last week there was a paper on arXiv which says that the reheating temperature, the lowest reheating temperature could be 5 MeV or so. Okay. So this is for the 10 MeV. Then we find the parameter space which leads to a detectable signal in each and every detector, while these gray shaded regions are ruled out because you will overproduce gravitational waves and they won't be consistent with BBN constraints. Similarly, the maroon one is about LIGO constraints. Okay? So I'm just showing one plot here, but in our GitHub repository, you have lots of plots for many transitions if you want to look at it. Okay. That was model agnostic. This is my last slide about a particular model. I also want to show you that it's not, you can use this framework to compute for your favorite model, whichever model you want. For example, last January, Joe Collinon's group in Oxford and Ed, they wrote this particular paper, which is called String Theory and the First Half of the Universe. So it's sort of string-inspired scenario, where you have inflation initially. At the end of inflation, there is a phase of kination. So there is an inflating field which decays into radiation, and then there is, let's say there is a moduli field which starts to roll over, and so there is a period of kination. So you go from, after inflation there is kination, and then the radiation takes over this stiff matter field, and the stiff matter tracks the radiation for a while until it starts to oscillate. The moduli field has a mass, and then it decays and reheats the universe. So this is a particular signal, a particular scenario. And for this scenario, I'm showing a typical signal. Okay? This is not all the possibilities, this is one possibility. So you have a long stiff matter dominated epoch, a radiation dominated epoch, a moduli oscillations and decay into, finally into radiation. And then we computed the range of parameters of this model, which will give you any signal in the ground-based detectors. Again, assuming the tensor to scalar ratio is high. And so this is that range that we found. So there are some models which could be, at least in principle, be testable by this. Okay? But you might want to relax the tensor to scalar ratio constraint. Why am I taking 0.001? You want to relax it. You don't want to see anything in V mode polarization. That's all right. In that case, your detection probability drops, and only in this, all the parameters in this white wedge are detectable. Okay. So if tensor to scalar ratio is very, very small, in fact, if it's much smaller than 10 to the power minus 8, no equation of state or duration of reheating can give you a signal in any of the gravitational wave detectors. Okay, so here everything shaded is not good observationally. Okay, just to show you this. Great. Conclusions are the following, that if there are multiple equation of states, then lots of different types of signals might come up purely from the vacuum inflationary fluctuations. And we did a model agnostic approach and showed how to apply it to a given model. But it can be done to more concrete phenomenological model. For example, string-inspired post-inflationary history. Okay. Our transition was smooth, but all transitions, cosmological transitions should be, our transition was instantaneous, but all transitions should be smooth at least by one number of e-folds or so. So we are now trying to work it out. And then the same can happen to scalar induced gravitational waves, which you are going to hear from tomorrow. So one needs to calculate that for multiple epochs. And also there will be lots of degeneracies. Since I'm creating these peaked signals, the peaked signals come from, let's say, first order phase transition bubble collisions. And so one needs to understand which part is inflationary vacuum fluctuations and which part is coming from, let's say, phase transitions or defects. I'll stop here. If you want to use our calculations, please have a look at this.
Thank you for this nice talk. We have time for questions.
Okay. So, so my question is that some point you said that for observation of these gravitational waves during the reheating phase, these low reheat scenarios are more useful. So, is there any intuitively, can we understand why is that? So, I couldn't get that.
Why is it so? Great,
Yeah.
Good question. I'll tell you a rough answer, okay? Imagine you have this tensor fluctuations which are frozen outside Hubble radius, and then they enter at some epoch. Let's say they're entering during reheating, right? During reheating, first of all, if your reheating equation of state is stiff, okay, then what happens is the background is falling faster than the gravitational wave energy. So it gains with respect to the background. Since omega GW is defined by energy of gravitational waves divided by background. Okay, so it gains. And if you have long period of reheating, then it gains a lot to reach some of the detectors.
So, so are you saying that it is independent of the potential I am considering? So, so always it happens like that. It is blue tilted.
No.
Okay.
So the potential, we need two things. The potential will set this height, you see here, which I have taken to be 0.001, but it could be relaxed. The calculation doesn't rely on that. Okay. The second thing is you also need to know the coupling of the inflaton to other particles and the subsequent couplings, which decides the width, the duration,
Yeah.
which we don't know in general. So that's why the model agnostic approach. But if you give me a particular model where I know the duration, then I can exactly calculate what the signal is.
Okay.
Is that okay?
Okay. Thanks.
More questions?
Thank you for the talk. In regard of these various different cases of the preheating history, it seems like the quite a bottom-up approach. And do you have any idea of how is plausible? How plausible is the possibilities in terms of the theoretical model building?
Like how feasible it is to have multiple equation of states during the heating or the duration?
No, I'm talking about, for example, the you may suggest the shape of a potential to realize such kind of various different stages of the reheating process.
It's not just the shape of the potential, but it's the couplings of the potential to other
Yeah, of
things,
course.
right?
Yeah.
So, for example, in this scenario here, the inflecton is quite strongly coupled and it quickly creates radiation right after inflation. But there are other fields, let's say a modulus field, which was stuck initially. It's massive, it starts to roll down, and it can dominate initially. If it's dominating, then it will create a period of kindness, and then it will fall below radiation and track it. So here is a situation where this can happen, but it depends on the situation.
Go ahead.
But as far as I understand, generically, in order to have the equation of state larger than 1/3, you have to have the high order potential, which dominate the.
That's one way, yes.
Yeah.
Yeah, that's one way. If you have a potential whose minimum, whose mass is somehow zero by protected by some symmetry or very low, then the oscillations around, let's say, more than 5/4, maybe 5 to the power n. Yeah, that's one way. Other way is if you have other fields dominating and they're heavy and they decay faster.
Yeah, so to me it seems like you have to have a quite complicated structure of the potential in order to realize to those various cases.
If it is just inflaton potential, yes. But if it's a modulus field like this, then not. In fact, this figure also appears in the review of string cosmology, which is Yvonne is here, and they say that it's quite at least generic for them. So,
okay.
Yeah.
Okay. Thank you very much.
Hi, thanks for the interesting. Just a quick one. Let's say you have this stiff phase in between after inflation, then you have this growth in the GW power, and then let's say you have this matter dominance, but let's say it's matter dominance effectively, but it's an oscillating field. So what will be the additional signal on that? Will there be oscillations in the spectrum, or? Let's say effectively it's matter dominance, but actually it's some oscillating field.
Yeah, those will be very fine features you can introduce. Yeah, so what is calculated is the average equation of state effect.
Yeah.
Yeah, but you can have a small scale time variation in the equation of state that will have features in the spectrum actually.
Okay.
In particular, you see this maybe quickly. You see that this is, let's say, a peak, right? Mm-hmm. This instantaneous transition that I'm doing should not be trusted at the peak, right?
Yeah.
So it depends on exactly how you realize the equation of state next to it.
Okay.
You may have an oscillatory signal there.
Yeah.
Right. So it should not be trusted there.
But the envelope effectively will be this, follow this.
Envelope would be like this. Yeah.
Okay. Thanks.
Just one quick question, okay?
Hello. So I have a small question. So can you go to the slide where you have written down the equation of motion for gravitational wave?
Equation of motion here?
Yes. So for your equation of motion, you have considered there is no source terms there.
These are vacuum.
Vacuum. Mm-hmm. So, but you know that reheating phenomena is a nonlinear phenomena. So there should be some source term. So
100%, yes.
So,
for example, if you form
then
oscillons,
yes,
or inhomogeneities,
yes.
They are very high frequency gravitational waves usually.
Yes,
but you would, yeah.
And another question is, so during throughout reheating, what we want to achieve? We want to achieve a thermal bath. Last, we want to achieve thermal bath because we want to create particle, and they will last. We will need a thermal bath. So you are considering during this reheating through this nonlinear process, your equation state is larger than the 1/3.
It could be larger than, yeah.
Yes, yeah, for your process. So how do we achieve from your 1/3 equation state to omega is equal to half, omega is equal to half to 1/3 equation state? How do we reach?
It depends on what is there in the universe, right? Equation of state is given by what is dominating, rho.
Yes.
Right? For example, here it is achieved by a moduli field taken over. But in general, it could be, maybe we should.
Okay.
Maybe you should, okay, if it's like within 30 seconds, if you can. I really have to move on.
Whenever you are plotting a spectra, that means you are fixing the tensor to scalar ratio.
In these plots, yes.
Yes. So that means you are also fixing the energy scale of inflation, and for a particular heating history, whatever stages you have a end of inflation scale, and primordial GW, first order GW, that will be suppressed after the end of inflation. So are you taking that cutoff scale somewhere?
Yes, it's here.
Okay, so it should be different for every reheating history, right?
Yes, yes. So for example, if I change my things, it'll be, this thing would shift the energy scale.
Right, okay.
Each diagram has its range as the maximum energy.
Okay, so the
Scale,
end of the line is basically your cutoff scale of
That's it.
inflation?
That's a hard cutoff, yeah.
Okay.
It should not be hard. You know it falls, and you know this. Right? It falls.
Yeah.
Okay, let's thank the speaker again, and let's move on to the next talk.